All right, here we go into limit section 2.4 this morning. Um, we're going to start off with a fairly brief discussion on average rates of change before we start to get into other types of rates of change tomorrow. Um, the average rate of change, I don't know, I guess it sounds complex, but it's actually pretty simple. It's where you just take your quantity and divide it by the time it takes to change. We know rates. Rates are change, just ratios in which we're measuring one change over another change. And in this case, the bottom is the time that it's taking something to change. Um, that's not really the case in this first example, where they just give us a generic function x cubed minus x. I guess we could say that it's representing time, but they didn't really indicate it. So I think we could really simplify this more to an algebra 1 problem. What is the average rate of change? Well, I guess we probably should start by coming up with a formula. So here is a little preview of where we are today and then moving into where we will be tomorrow. And this is a little snapshot from a couple years ago, about 2 years ago this time. You were studying circles in geometry. I happen to know this because I just gave this lesson recently in geometry. Um, we talked about the relationships that lines and circles can have. And I don't know to what extent you remember the names of these lines, but just as a recap, uh, this dude right here is called a secant line. And the reason it's called the secant line is because it intersects the circle twice. Keep that in mind. And we will be discussing this dude more tomorrow. So back to our formula. We're trying to find a formula, and we would like to find the average rate of change of this function. It looks kind of like a cubic function, but who really knows? It's just a generic function, but over the interval AB. So the first thing I want you to make sure you understand is that this is not a point. If it was a point, it would have the curvy parentheses on the outside, not the brackets. The brackets indicate it's an interval. So it's saying what is the rate of change from point A to point B. So they give us a couple points here. So I guess this x value we're calling A, and this x value here we're calling B, right? Well, I think that in Algebra 1, we used to find the rate of change between 2 points by using this formula right here. Remember that guy? Changing y over changing x was y minus y over x minus x. I think we called that the slope formula, didn't we? And it was just a constant rate of change of lines. Lines never had any kind of differing rates of change. Well, that's not true once we get away from linear functions. Once we get into the polynomials that are above degree 1, so squareds, cubes, and so on. Once we get into any other of the parent functions we've studied, like root functions or rational functions, or exponential functions or logarithmic functions, etc. I guess absolute value functions are fairly consistent, except where they change direction. But check this out. At point A, if you think about where this function is moving, it's actually kind of moving down just a little bit, isn't it? Just a tiny, tiny bit. This is the direction it's moving as it goes, and then it flattens out probably just a little bit more to the right, and then it starts moving up towards our second point, where x is equal to b. And at every point, along this line, at every point along our curve here, woo, at every point along this curve, we get just a slightly different rate of change. Um, at this point, the curve is changing steeper than it was before, but if I went a little further, if I went just a little further up, that would steepen up just a little bit. But then it could fly back out, and then it could turn around and come back down, and it could be decreasing. But the point I'm trying to make here is that all of these different points, we get totally different rates of change at the points. Okay, and that's something we really never talked about with lines, because lines always had the same rate of change at every point. They never changed direction. They never changed how fast they were going. But curves do. They're faster sometimes. They're slower sometimes, and so we keep track of that. Now, the average rate of change just says if I took all of those rates of change throughout, this interval, so from the point where it seemed like it was almost going down just a little bit to the point where it was kind of slow, and then to the point where it was speeding up all the way up to this point, all those different rates of change, all those different slopes, think of it, there'd be infinitely many of them, wouldn't there? Because the density of real numbers tells us there's infinitely many points between A and B. So that means that there's infinitely many points on our curve, which means there's infinitely many different rates of change. Well, we certainly can't keep track of all of them. But what I can do is I could take the very first rate of change at A, which I think the Y value at that, if I plugged, right, I'd be plugging A into f of x. So just A into f of x to figure out the y value. So let's just call it f of A, okay? And then, of course, the y value for point B would be f of B. Okay, so the rate of change as we move from the point A, f of A, to the point B, f of B, is really just that purple line, that slope, which I guess I kind of revealed a little sooner than I wanted to, but it's really just the line itself. So the average of all of the rates of change in between is just, um, it's really just the slope of that line. And so if I come down here and just make some slight adjustments to our y minus y over x minus x formula, we get um, what we'll call the average rate of change formula. So for for x1, y1, we could call those f of b and, and b, and then for y2, x2 and y2, we could call those a for the x, and then of course f of a for the y, and you have yourself a formula. Okay, f of b minus f of a over b minus a. A lot of books will have x2 minus x1 over y2 minus y1 for the slope formula. And so what they're telling you is it doesn't matter which point you call point 1 and point 2, you'll still get the same slope. I guess we could make the same argument here. We could do f of a minus f of b over a minus b and still get the same average rate of change. So keep that in mind, that you don't have to know which point is A and which point is B. Usually the point that you start at to the left is A, and then B is to the right, but you could subtract them in a different order and still get the same answer. So this brings us back to our original question. Over the interval, and it was 1 to 3, right? Over the interval 1 to 3, what is the average rate of change of this function x cubed minus x? And you should be able to find this example right on page 18 of your notes. And notice they didn't give us any y values, so we have to kind of figure those aspects out, but not a big deal, right? We can plug 1 in to x cubed minus x. It'd be 1 minus 1, wouldn't it? Just 0. And if we plug 3 in, we get 27 minus 3, so that would be 24. So now we have our x's and our y's. So if you're thinking to yourself, isn't this just finding slope? Isn't this just basically algebra 1? You'd be absolutely right. By the way, notice I did this one as f of a minus f of b. So I did it kind of in reverse. And I just wanted to show you we get the same exact answer. In this case, what would we get? Negative 24 over negative 2, which would be 12. Um, and if we did it with the f of b minus f of a formula, we would still get 12. We get positive 24 over positive 2, which is still 12. So that should be worked out for you in your course pack already. Example number 1. But that's what average rate of change really is. Average rate of change, we're going to find, is just slope. So after all that discussion of all the different rates of change along a curve, it just comes down to slope. All right. Hey, what the heck's going on here? I'm sorry, it's kind of gross. All right. So these are the kind of how the first 6 problems are going to look for you on tonight's assignment. It's going to give you a function, and it's going to give you a couple intervals, and you're going to find a couple rates of change. Now, I do implore you, these are not points. We just had this little discussion, right, that these are interval brackets. They are not points. And what I see a lot of in the past is people will just say, oh, this is one point, this is the other point. I'm just going to find the slope between these 2 points. But that's not what they're asking. They're giving you the x values where you're starting and ending. So this is like your a, and this is like your b. So you're going to have to plug those into your function to figure out the y values, and then you can use the f of b minus f of a over b minus a formula. Okay, so for 6 problems, you're basically just finding slope. You will have to generate the y values, but seriously, you're doing algebra 1 work. So enjoy it. Moving, holy cow, this is starting to get ridiculous. Hold on one second, please. It's getting out of control. I see. We're doing a problem about flies. Now that explains it. So what do we got here? Fruit flies. Experimental biologists often want to know the rates at which populations grow under controlled, that's better, laboratory conditions. The figure below shows the number of fruit flies that were grown in a controlled 50-day experiment. So especially on my screen, hopefully it's a little clearer on your workbook page, because you do have this same graph, and it looks like this. Holy cow, all right. So you can see that over the first 50 days, we started with very few fruit flies, maybe just a couple. And then by the end of the 50 days, we were just under 350. Think about the nature of this curve. I mean, these are probably discussions you had in your science classes over the years, where we have population that starts off really slowly when we just have a couple of pairs of these flies, but as they get used to their environment and start populating, co-creating, so to speak, right? Suddenly, that growth is going to really start to take off. It's going to start to increase. It's going to get faster and faster. Now, if there were unlimited resources and unlimited room, maybe it would just keep doing that forever, right? But of course, that's not the reality um, of a finite world. And eventually, room and resources start to run out, and then that growth eventually starts to slow down. Okay, and if it gets really bad and there's plague, starvation, that kind of stuff, it could actually really start to drop off. But in this case, you can just see where it sped up and went down, and we could have that same conversation we had previously, where we've got really slow rates of change, and then faster rates of change, and then fastest rates of change, and then slower rates of change as we get through here. Look at all those different slopes along the way. That's really the conversation that we're moving towards. Okay, but if you go back and look at the question they asked, which was, what is the average rate of change between the 23rd day of this experiment, so that's this day right here, and the 45th day of the experiment, which is this day right here, there's your average rate of change right there. It's just the slope of that line. a line that intersects a curve twice. If we go back to about 5 minutes ago, when I just like randomly flashed a picture of a circle at you, I think we call that a secant line. So another name for this type of slope is a secant slope. Secant slope really is just the same as average rate of change. You can think of it that way, okay? So that's the simplest what they did. Now, there was no formula here. This was just reading the graph and saying, all right, 23 is about 150. And at 45, it looks like around, well, it's definitely a little less than 350. So they came up with 340. So they just approximated those, okay? And you'll have a couple problems like this where you'll be reading points off of graphs today. I would expect everybody's answers to be very similar, but perhaps not exact, because we are approximating on some of these points what they are. But that's the end of that problem. It looks like 9 flies per day is what they ended up with. They just used that same formula. I mean, you may still be thinking of it as y minus y over x minus x, which is pretty accurate, but because we're calling the interval AB from 23 to 45, we did f of b minus f of a over b minus a. There you go. Boom. Slope. That's all it is, right? Now, this problem extends a little bit. They really use this fly population as a driving force for the argument where we take average rates of change into the big idea tomorrow, which is going to be called instantaneous rate of change. And so this next picture, okay, probably on page 19 by now is where you find this, right, in your course pack, shows you the problem we just did. But then we start doing this thing where we find the average rate of change over smaller intervals. All right. So once again, let's blow this up. I mean, if we read through here, it says we may also want to know the rate of the population on day 23. Think of that. So we're not saying what's the average rate of change from 23 to 45 or from 23 to 40, but on day 23 itself. That's a huge concept. And this is something we'll talk about tomorrow, where you were never asked to figure out something like that in algebra. I mean, if it was a linear equation, it would be the same as the slope of the line, because once again, the rate of change never changed. It never differed. It was always a constant. Well, only lines have that property, right? No other types of graphs have a constant either growth or decay. So this is a very new type of question that would be asked of you. This is their method of trying to figure that out. They are going to keep taking these secant slopes, but what they're going to do is they're going to take that second point, they're calling it Q, and they're going to push it back toward that original point P that we're so interested in, find the rate of change at that point. Okay, so here's a larger picture of this, and you can see the different slopes that are being pushed back as we go from 45, right, to 40, to 35, to 30, as these points are pushed back along the curve, we get slightly different slopes. And the big theme tomorrow, the big thing that we should realize, is that these slopes, as we get pushed back, should be getting closer and closer to what we really want to find. And what we really want to find is this slope, which only intersects the curve at a single point. Huh. That should bring us back to the very beginning of this lecture again, to that random picture of the circle, which, hey, one of the lines hit it twice and one of the lines hit it once. So if you remember what that's called, then you will know exactly what we're talking about tomorrow. But this is the emphasis of tomorrow, is to try this little game and see what we come up with as we push secants into this type of line, okay? And so a couple problems tonight. You'll be given a graph like this, like I said, and they'll start you at a distance from the point in question. And then what they're going to do is they're going to ask you to find a number of secant slopes. I think 4 per problem. And so you'll find it, at 45. You'll find the slope at 40. You'll find the slope at 35. And here's their work, y minus y over x minus x, or f of b minus f of a over b minus a. And this was the first one we found, I think, when we were at 45 was 8.6. But then it got a little steeper, right? And then it got a little steeper. And by the time we get to 30, so that was right here. Remember, 23 was right about here, right? That slope of 16.2 is starting to actually get pretty close to the slope that we're trying to find. So that's, that's comparing this line right here um, and if I just tweak it a little bit, that's the one we're looking for. So you can see it's a lot closer at 30 than it was way out here at 45. Those slopes are getting closer. So that's tomorrow. And I mean, you only have 8 problems tonight. So since this lesson wasn't too bad, I'm going to try to give you a little bit of a push into what we're talking about tomorrow. By the way, the rest of this table and some of this work and explanation is on your course back, so I think you're fine. But just so you're clear on problems 7 and 8 tonight, use the chart and find the 4 different slopes they ask you to, and what you're trying to do is you're trying to see what kind of a pattern you see within those slopes. They should be approaching something, and see how you do with your accuracy when we go over it tomorrow. But that's a big idea of our conversation tomorrow. Okay, so like I said, short lesson, so I'm gonna give you a little bit of a head start into tomorrow. Okay, just a little bit, and here we go. This is algebra 1, obviously, slope. We learned, hey, rise over run, y minus y over x minus x, right? And we spent, boy, a lot of time in algebra 1 on that because that's how important it was, right? And then these flies all over. We kind of moved into this, change in y over change in x idea. Although looks like they have change in x over change in y here, which is really weird. In change in y over change in x today, we converted into what we're calling an average rate of change formula, which is really still just y minus y over x minus x, but we're using it to define the average rate of change over a specific interval, so we're calling it f of b minus f of a over b minus a. A little more specific than just a couple y's and a couple x's. The x's specifically are an interval that we're interested in finding the average rate of change on. So this is all old stuff or into slightly new stuff, right? Um, Still all based on just our slope formula. Well, this is also going to be, okay, this is a slightly new picture. And the only difference is that instead of just saying I have, point A and point B, or point, X and point X1, X2, I guess is how we would do it in algebra 1. We're gonna keep the original X. We're gonna keep the original X here as part of our new point, except we're going to describe the new point with how far it is away from the original point. And most of the time, most books, our book calls that h, just a value h. It's an arbitrary number. Usually it's defined as an arbitrary small number, but it could be as big as you want to start with. Really, it just, if you make it too big, it wastes your time. You want it smaller than not. Like on the example we just looked at with the graph of the fruit fly population, if you go way too far away, it's going to take a long time to push those secant lines back, right? So we usually like to keep h smaller, but x plus h just describes how far our original point had to move this direction to get to the new point, okay? Now, that means that our y value when I put x in is going to be f of x, and that means our y value when I put x plus h in is going to be f of x plus h. So I have these 2 new points now. X, f of x, x plus h, f of x plus h. It looks a little uglier than just, a and b, f of a, f of b. but it's really the same thing. Now, some books will, instead of H, they'll call this delta X, so change in X, which also makes sense. And you'll see that from time to time. It really just depends on the book you're using. Um, I would say more books probably use H than delta X, but you certainly could use, you could see delta X just as much. But this picture right here sets up a slightly different way of looking at our formula. This is the one we built today, right? This is the one where we said, oh, that's going to be f of b minus f of a over b minus a, okay? And that's your average rate of change. So using this formula right here, and I'll make a slight change. Instead of having these x's in here, since this one was using a's, right? I'll change these x's into a's for us, okay? Let's go ahead and change this formula that we already have. Let's change that using our new points here. So where instead of the point to the right being b f of b, it's a plus h, right, for the x value, and f of a plus h for the y value. And as you can see here, they're already doing the subtraction to find this change in height over here. The first point, the first y value was f of a because we put a in, right? So it doesn't really look any prettier than this. I mean, it looks uglier. This, I think, you would almost certainly would say would not look as nice as this. But although the top doesn't change at all, right? The bottom actually becomes very nice because since we built the second point using the first point, since we, built a plus h using a, what's going to happen to those a's right there, right? And so this f of a plus h minus f of a over h looks kind of weird, but it's no different than f of b minus f of a over b minus h, just written in different terms, and it has a very specific name. It's a famous mathematical way of expressing the average rate of change, and it's called the difference quotient. So this is the difference quotient. And if you Google difference quotient like I did, and then just looked at some of the images that pop up immediately, right? Here is the same thing that we just did, and then look at this. Same thing. Look at that. It has the slope there, the secant slope, right? F of x plus h minus f of x divided by h. I mean, we used a instead of x, but you can see it's just a matter of what are you going to call that x value? You're going to call it x, or you're going to call it a. Here's another one. Okay, they have it actually labeled here, the secant line, right? Because it's hitting our curve twice. Okay, there's the distance between the first point and the second point is h. There's that difference quotient. Okay, and that is going to be something we use tomorrow. You don't need to use the difference quotient tonight, but I just wanted to give you a little jump forward into tomorrow. And you only have tonight, hopefully no flies, but only 8 problems, like I mentioned, on the new PDF worksheets that are going to be attached. So enjoy some Algebra 1 tonight, and tomorrow we'll talk about a new and entirely different kind of rate of change, which obviously we're already hinting about today. All right. Thanks for listening, and we'll talk to you soon.